Welcome back, everyone. We just started a section on weak convergence with this introductory comment here. So if you're in the Hilbert space of square summable sequences, then the sequence formed out of the basis vectors E sub n is not going to be convergent in the ordinary 2 norm on the Hilbert space. However, nevertheless, for all linear functionals on the Hilbert space, well, first off, Rie's representation tells me that these linear functionals have a particular structure. They're all inner products with a unique element y that depends on f in the second entry. And now I claim when n goes to infinity, this will go to 0. And why is this? Well, this is because of Bessel's inequality. Bessel's inequality. So remember Bessel's inequality, there was if you have an orthonormal set, like the ENs, then it was a statement on En, say x squared, n1, say capital N, less than or equal to the norm of x squared, and that thing held for all vectors x in your Hilbert space. So now, since the right-hand side is independent of capital N, you can, of course, push n to infinity. So you will also have this statement in the limit. And that's the one that I'm applying here, right? So I'm going to substitute in now here my the ENs, right? The same ENs that I have up there. These, the statement of the Bessel inequality, that's valid for any orthonormal set, not necessarily those ENs up here in L2, right? But nevertheless, now I'm using it for those ENs. And then why does this inequality yield this? Yeah, because if capital N goes to infinity, then you have a series on the left-hand side. And the Bessel's inequality tells me that that series is convergent, right? That there's an upper bound for it, the norm of x squared. And, well, the necessary criterion for series convergence then kicks in and then tells me that these guys in here, they have to necessarily go to 0 as small n goes to infinity. And that's precisely what's written down there once you replace x by this element y sub f. All right, that's why Bessel inequality tells me this. Okay, so what we have gathered or what we have found here is that although that sequence E sub n up there does not converge in 2 norm, if you evaluate it on any bounded linear functional, then that thing goes to 0. Okay, and that motivates the new notion of convergence, which is called the weak convergence. So definition: a sequence xn in a NLS, either over the field of real numbers or complex numbers, converges weakly to a vector x if and only if for every bounded linear functional we have the ordinary convergence fxn to f of x in the underlying scalar field as n tends to infinity. All right, so that's the notion of weak convergence. So in this example up there is one example of a sequence that converges weakly, these ENs in small L2, but does not converge in the ordinary 2 norm. Okay, good. Weak convergence is very important. It gets its own symbol. I prefer to write it like this. So I make a horizontal straight line and then sort of half of an arrow, sort of poor man's weak arrow, like this. Xn goes to x as n tends to infinity. Sometimes in other books you will find an arrow with a W on top for weak, or other notions. I will use the one in blue. Okay, so that is the weak convergence. Okay, now having this, now we will gather the basic properties about weakly convergent sequences, right? So you have noticed now we have to go back to our knowledge on dual spaces. The last section with bare category didn't use, well, there was one example where I visualized that in principle of uniform boundedness you need the completeness of the space. I gave an example that was dealing with linear functionals, but beyond this, linear functionals did not appear explicitly in the last section, but they appeared heavily in the section before that and in the section on the Hahn-Banach theorem. But now we're back at it. Okay, so theorem, let X be a NLS and Xn a sequence if Xn converges, well, in norm, so the ordinary convergence, as n goes to infinity, then it converges weakly, right? So that's why really the name weak is justified. And this is not a two-way street. I gave an example with those ENs in little l2. Okay. Furthermore, although weaker, it still shares some of the fundamental properties of ordinary limits, namely weak limits are unique. So if a sequence converges weakly to something, then it can only converge to one thing. And convergent sequences, they're all bounded, right? And the same is true, and that requires principle of uniform boundedness. The same is true for weakly convergent sequences. So if that sequence converges weakly, then there exists C positive so that Xn less than or equal to C for all members of the sequence. Okay, that's it. All right, so let's prove it. First, how does norm convergence imply weak convergence? Okay, that is the standard argument. Look at this. Use the fact that you're dealing with something linear. So you have Xn minus X, and now use the standard estimate that we have applied multiple times in this course. Operator norm like this, and this is valid for all linear functionals here in X star, right? So now if you have the ordinary convergence, this right hand side as n goes to infinity will go to 0, hence the left hand side goes to 0, and that's precisely the weak convergence, right? So let's write this out. We see that Xn converging ordinarily to X implies weak convergence. And again, I said it before and I've done the example, the other direction is not true in general. There are actually some Banach spaces where this is if and only if, but this I will mention at a later point in the module. Next, if Xn, this is a special property. If you have a Banach space where weak convergence is equivalent to the ordinary convergence, that gotta be special, and it is. And we will mention it later on. Okay. Now, about the uniqueness. If you have, well, Xn converges weakly to X and Y, as n tends to infinity, then, okay, I'll write it a bit funky like this. So fx, and then on one hand it converges to f of x, and on the other hand it converges to f of y. Okay, both as n tends to infinity. That looks weird. So f of x equal to f of y, and this is valid for all bounded linear functionals, right? Yes, so but now how can I now conclude that x is equal to y? Well, you might have noticed that So far we haven't used one of the consequences of the Hahn-Banach theorem. Okay, there were so many, so it's a bit hard to keep track, but one of the corollaries of the Hahn-Banach space was the, not Hahn-Banach space, of the Hahn-Banach theorem was the separation property, which goes as follows. So if you have two distinct vectors in a Banach space, then the dual space is going to keep them distinct, right? So that is to say, if x is different from y, then you can find a linear functional f such that f of x is different from f of y. Now, if you negate that statement, then it says if f of x is equal to f of y for all bounded linear functionals, then x has to be equal to y. And that's precisely what I need now, right? So f of x is equal to f of y for all bounded linear functionals will give me x is equal to y. Okay. In turn, by the separation. Okay, I will just start by a corollary of the Hahn-Banach theorem, x is equal to y. So, and that's the uniqueness that you want. All right, now the last thing, the exciting one. So if you have weakly convergent sequence, why are those terms all bounded in norm? So, and that will be principle of uniform boundedness. So finally, now this is a beautiful application of the canonical map that maps you from a normed linear space to its bidual. So finally, using the canonical map J from X to the bidual, well, remember this guy sends a vector x to this linear functional that acts on linear functionals in the following way. Jx of f is pointwise evaluation at x, where x for all f in x star. We know that J is an isometry, capital J is an isometry, and this just meant this. Okay, so now having recalled this, for all f in the dual space there exists constant c, which of course can depend on f, so that fxn is less than or equal to c for all n in n. And why is this? Well, because xn converges weakly to x, right? So that simply means this is the ordinary convergence in the underlying scalar field of fxn going to f of x, right? And convergent sequences in the real number field or in the complex number field, they are surely bounded. And that's precisely what I write here, right? So there exists this constant c, which is independent of n, because the image sequence is bounded, because it's a convergent sequence in the scalar field. However, the constant might very well depend on the linear functional that you're using there. All right, so you have this for all n in n. This shows that for each bounded linear functional, you have supremum of j xn f, and the supremum runs over all n is finite, right? Because remember, this here is precisely fxn, and this is finite because of this, right? Yeah, but now you should realize that this is precisely the pointwise boundedness of the family. It has the family f jxn indexed by n. This is a family in here, right? So this is, remember this is bounded linear transformations from x star into the underlying field. And notice here, I've not assumed in my theorem that I'm working in any complete normed linear space. It's just a normed linear space. And now you see why I don't need this, because this here is always a Banach space. And so is our underlying scalar field, right? And that's the only thing that I need for an application of the principle of uniform boundedness, that the domain and codomain spaces are complete. And they are here because I work here with a family of elements in the bidual, right? So that's why this is enough. You don't have to assume completeness here of your normed linear space, okay? So it has this family is pointwise bounded, is pointwise bounded. Well, given that, that's what I just said, the dual space is complete, is a Banach space. This we proved in the very first week of this class. Given that X is a Banach space, I will just say PUB, principle of uniform boundedness, asserts that that family is uniformly bounded. So in other words, supremum JXN, supremum taken over all members in the family is finite. Yeah, but that's not where you use the isometry, right? This is precisely the norm of Xn. Okay, and now you're done, because it says exactly what you want, that there exists constant C such that the norm of Xn is less than or equal to C for all n, right? Because the supremum there over all of these guys is finite. And thus there exists C positive so that Xn less than or equal to C for all n. So that sequence here is bounded in the norm. Okay, good, that's it. So, having established now the first basic notions here of basic properties about weakly convergent sequences, now one can ask, how do you check if something is actually weakly convergent? Well, here's a sort of helper. Let X be a normed linear space and Xn a sequence in it. Okay, then Xn goes weakly to X as n tends to infinity, provided two things are satisfied. Well, that first one shouldn't maybe come as a surprise, because that's a necessary criterion for weak convergence. We just proved it. There exists C so that the terms are bounded, right, in norm. So that's a necessary criterion for weak convergence. We just proved it. And two, now that's more it. So it is enough to check the weak convergence on dense subsets. There exists a dense subset M of the dual space so that you have weak convergence on that dense subset. Okay, for all F in M. Right, that's precisely what number 2 says. So having weak convergence of a dense subset plus number 1 here, this uniform boundedness of the norms, gives you the weak convergence. Okay, it's not so surprising because you're dealing with continuous things, and there in general it's enough to check something on. You're dealing with continuous linear things, so there usually it's enough to work on some dense subsets and then lift it to the whole thing, and that's precisely what this thing says. So how to prove it? Well, that's easy. Pick arbitrary linear functional in the big thing, then density allows me to approximate it well enough by something in that dense subset. This is always the standard move in the game. So, and this is convergence in the dual space, meaning in the operator norm, as M tends to infinity. Note that for all n, m natural numbers, now you want to say something about this guy, right? That is the kind of difference that you want to make small. So what you do is you insert successively terms for which you can say something, right? So you squeeze in that m, fm, xn, and then fmx plus fmx minus f of x. Okay, ordinary triangle inequality in the underlying field. And now again, here you use that this is f minus fm on xn. This is less than or equal to f minus fm, and then the norm in x. The second one you leave for the moment, and for this one you use the same argument that this is at most operator norm f minus fm and then x in x. Okay, good. And now why do I do this? Well, because I have perfect control over these green underlying things because of this, right? So this goes to 0, and notice here, this is property number 1, says that this can't escape off to infinity, right? It is bounded by this property here, right? So you have control over 2 out of the 3, and now of course you also have control over the second one, because, well, you assume weak convergence up here on the dense subset, right? And that's precisely what you use here, because the fm's are from m, and you have weak convergence here, right? So this here for a fixed m, as n goes to infinity, this goes to 0 because of the assumed weak convergence on the dense subset m in the dual space, right? So, and now you have, you know, everything that you want, and the left-hand side does not depend on m, so you first, well, you know, do the epsilon thing. So I've written it out in the notes. Okay, maybe I will now write it out here too. So, but that's the idea, right? So with, first off, xn is bounded, and of course if you fix a point, that point also is gonna be bounded, and you can choose here the same c, right? You can optimize the c in such a way that you have this inequality both for the xn's and for the x with the same c, right? Now, as I said it in Word, let epsilon be arbitrary, and then by fm to f there exists capital N which depends on epsilon, so that in operator norm this here gets small. Then here's some cosmetic surgery, not epsilon but epsilon over, well, 3c. Okay, and likewise you can, without loss of generality, assume that the c is different from 0. If c is equal to 0, all the xn's are 0, and then there's nothing to show here. And likewise, this is because of the weak convergence on the dense subset, fmx also less than epsilon over 3 for n at least capital N. Hence, for all mn at least capital N, fn of x minus f of x. So I had it shaded in colors on the last thing. There was this norm that you control by this. Then there was that norm of xn that you control by c. Then the middle term, you use the reconvergence on that dense subset. You get epsilon over 3. And of the last term, very much like the first term. And that's why the cosmetic, because the c's, they go out. And 3 times epsilon over 3 gives you epsilon. Right? This shows xn goes weakly to x, since the bounded linear functional was arbitrary. Okay, and that completes the proof of this. There is, next to the weak convergence, another convergence which is dual to the weak convergence, and that will be the last thing that I write in this video. And we will study this type of convergence and its relation to the weak convergence in the next video. So if you instead take a sequence of linear functionals in the dual space, well, dual space is also a non-linear space, as we know. It's more than that, it's a Banach space. In the dual space of a NLS is, well, weak, and for the lack of a better word, I call it weak star convergent, if and only if, star indicating that I'm dealing here with sequences in the dual space, if and only if for every x in X we have Fn of x going to f of x as n tends to infinity. We write, well, Fn, again sort of half an arrow, and then I make a star on top, to f as n goes to infinity. All right, so this notion is really dual to the weak convergence, in that in the weak convergence it was xn goes to x, so the index was on the x, not on the linear functional, if fxn goes to f of x. Now here the role of x and f are sort of swapped, right? I look at sequences of linear functionals, and they are called weak star or weakly star convergent if and only if for any point that you evaluate on, you have fn of x going to f of x in the underlying scalar field. All right, that's the weak star convergence. Excuse me. Now in the next lecture we will see how these two notions relate to one another. We will study examples, and then, very much like how we did it just now for the weak convergence, we will gather basic properties of weak star convergence sequences. And then there's two big theorems in this section. They are sort of Bolzano-Weierstrass type theorems. So Bolzano-Weierstrass in real analysis or complex analysis deals with certain bounded sequences and the fact that these bounded sequences have some convergent subsequences. Now here, Bolzano-Weierstrass type theorems that we're going to discuss are dealing with weak and weak star convergent sequences, right? So they're more complicated, but they're mighty useful. But all of this will come in the next and then in the following video. I'll see you then.